we've gotten to a video where the details aren't coming so fast and furious. Would like to show you some tips about visualizing heat transfer on the TS diagram. So it's simple as that. So just want to give you some reminders about how you can use the TS diagram to your advantage rather than kind of saying, oh, shoot, they've told me I have to draw a TS diagram. What good is that? Looking at the TS diagram can really help you get out of some jams by visualizing heat transfer on the TS diagram. So we'll go right back to the basic fundamental definition in chapter 6.6 of your textbook. Should look familiar. So remember, ds, incremental change in entropy, is del Q over T, incremental heat transfer, as long as you evaluate that across a reversible path, internally reversible path. And what that led us to was seeing that the heat transfer in, let's say from process 1 to 2, so overall kilojoules, kilowatts, kilojoules in is equal to the integral of TDS. And so I try to say, integral of TDS on a TS diagram, that's the area under the curve. And that's what we want to review a little bit about this, the power of looking at the area under a process path curve on the TS diagram. 3 examples for you. So I've written down that fundamental ds is del Q over T. Okay. So we're looking, so what's the area under the curve for this isentropic process? And so it's 0, right? And so Qn is 0. It's a vertical line. So isentropic means constant entropy. And so, for example, what if in a quiz or test, you're given a TS diagram and not given the words, not given the phrase isentropic process? You're not given it's fully reversible and adiabatic, not given that, but you're given a process 1 to 2 with a filled in straight line going down or up. That tells you it's, as long as it's a reversible process, meaning a straight line, or not has to be straight. A smoothly drawn line can be a curve or a straight line. That would be reversible. So if you've got the process path, you can visualize the area under the curve. So this 1 to 2, it's a no-brainer. Qn is 0. Okay, now we've got a reversible isothermal process. Both of them. Okay, process 3 to 4, we're increasing our entropy at constant temperature reversibly. Do you see that the area under the curve is a positive number? You're adding heat. 3 to 4, you're adding heat. And with your eyes, you see that the amount of heat added is that rectangle. Okay, great. Something to put in the back of your mind for quiz and test time. Process 5 to 6. It's occurring at the same temperature, but it's going right to left. In other words, what will the area under the curve from 5 to 6 be? It's going to be less than 0. You're integrating right to left. You can see with your eyes what the heat transfer is. It's that rectangle, but it's going to be a negative number. And so that's really kind of a point that I want to make in this video, is that if you're given a TS diagram and given the process path shown as solid lines, it doesn't have to be a straight line, just a solid line, that means the process is reversible. Process path is known. Okay, so can be very powerful in visualizing heat transfer on TS diagram. Okay, and I just made my point here, visualizing heat transfer for a reversible process on the TS diagram. And what I've tried to just cover was this section 6.6.1. So that's what I tried to illustrate, maybe in a easier to understand way, I hope. Now for a reminder, I'm trying to foreshadow some things that are coming up. A reminder of the difference between capital Qn and little qn. And so this has to do with both closed systems and open systems. So for a closed system like I sketched here, you've been dealing with capital Q, and you know that the mass of a closed system is constant. It's m. And so in the textbook, we have, and some homework problems, we define little q in kilojoules per kilogram. So I'm jumping down here. So recognize what I just showed is capital Q in on a TD little s diagram. Capital Q in is going to be the mass times the integral of TD little s. That's a little bit of a point I'm trying to make here. Okay, so if you've got T times little s diagram, you're going to need to know the mass. All right, so but also recognize that little q in is defined for a closed system as Q over M. Another very common situation in engineering and the rest of this course that you're going to have is little q in for an open system that's steady state, steady flow, and there's only one inlet and one outlet, kind of like a steam turbine, an air turbine, an air compressor, a pump. All those things are one inlet, one outlet, and typically we treat them as steady state, steady flow. And so do remember, back of your mind, little q in for an open system with this model is Q dot in divided by M dot. So let's jump down here to the bottom. Do you see that Q dot in is going to equal M dot, the mass flow rate, times the area under the curve on the TD little s diagram? Okay. And so that's got some value for you. Looking ahead, it's so easy to get very confused when you're dealing with open systems and you're dealing with little q and little w. So many students get confounded on that. They get so frustrated. And I'm trying to provide just some tips about getting more comfortable with little q in for open systems, steady state, steady flow, one outlet, as well as closed systems. So notice here, my arrow is pointing, so I can have both an open system and a closed system, and I can still make the fundamental Q in across an internally reversible path is the integral of TD little s. And that brings us to the end of this video where we didn't do any computations. We simply visualized things. And so the big takeaway here is that you can visualize heat transfer on a TS diagram for any internally reversible process as the area under the curve. So that's the big takeaway. Okay, I hope that helped. No number crunching, no problems, but just tried to, at this point in the class, at this point in Chapter 6, need a little reminder of when the textbook and homework problems talk about little q in for open systems. What's all that about? Hope that helps.